let's talk assembly, right? Loads of fun. And just for the sake of demonstration for this, I'm going to have you guys write it on this at least first piece of code. We'll just use Easy6052, although I will show you a couple of other ways, to do it, and then we'll sort of transition to doing assembly programming for two different pieces of hardware. The breadboard thing, which Evan had an epiphany, which I don't think I quite thought about, which was the announcement I sent out, namely that maybe actually the problem isn't anything. It's just that the sockets that I got, the little pins on the underside, maybe they're not actually making contact with the breadboard. So he removed the socket, put his EEPROM straight in, and guess what? It started working. And so, yeah. Okay, so try taking the socket out and replacing it with the EEPROM and then see if it works. Okay, now be careful, obviously, when you put the EEPROM in to not over force it, not under force it, and then make sure you use the chip puller to carefully extract it when you need to reprogram it. That was the whole point of me getting the sockets in the first place, was to avoid that. And then, so other piece of news is there is somebody who basically designed PCB versions of this that we could just solder the components to. So I ordered those from PCB Way. So they shipped from Shenzhen, China, I think yesterday. Maybe they're on their way, but they're coming literally from China. Um, Fortunately, they don't have to fly over the Ukraine to get here. So, yeah, so those will show up eventually. And when that happens, then I'll chain Rippy to a table upstairs in the lab, and he'll solder them together, or at least one of them, and we'll test it and make sure it works. But there, we will use the sockets, because the little pins on the outside of it, right, those are designed for going into holes on a circuit board and then being soldered to. And I think they're just not quite long enough to get into the holes in the breadboard and make good contact. And of course, if all of them don't make good contact, it's not going to work. So anyway, uh, okay. So basically, I'll have you guys do one assignment, which we'll talk about some of the details here today, for doing the old Fibonacci's recursively and iteratively in 6502 assembly. And for the sake of that, we'll just use Easy6052 here because we've got the monitor and everything. It's real easy, hence the name. But then what we'll transition to is doing the assembly programming for two actual machines. One would be the breadboard, okay, and two would be the getting back to the Commodore, okay, and doing this live on real Commodores with actual disk drives and stuff. And doesn't that sound fun? Okay. All right. So today, what I want to do is sort of talk a little bit about the assembly and go through an example, an iterative example and a recursive example, both in straight assembly, but then also I want to talk about, at least with respect to the Commodore, that it is possible to use C to kind of, well, cheat's not the right way to put it, but so you remember when we, in 241, right, we could use C to generate some assembly, machine-produced assembly code, and we were able to learn some things from that versus hand-produced assembly. Well, we can do the same thing. There is a C compiler that will spit out 6502 assembly. It's called CC65, and not only will it do that, but it can also output program files that go straight onto the Commodore, okay, which is nice. So we can use that as sort of a middleware piece of glue, at least initially. Right. Okay. So wanted to talk through a couple of examples of doing something iteratively and something recursively. Okay. Now, what's the assignment going to be for this? The Fibonacci's, yet again. You guys are probably sick of these dang things, right? But they are classic, right? Which is why they make for good assignments. Okay. Well, so in 241, what was our example of an iterative or recursive thing? That was what we did in class. And then you guys did the Fibonacci's as an exercise. Yeah, we did the factorial. Okay. Now, since factorial is defined using multiplication, and we don't have a hardware multiplier on the 6502, I don't want to do that. So instead, I'm going to do the triangular numbers, which are like factorials, but you add instead of multiply. And that way I don't have to worry about the multiplication part. But otherwise, there's really no real difference. Okay, so like we did with the Fibonacci's or the factorial, we can think of this iteratively, or we can think of it in a recursive way. And while I would not actually use the recursive way for computation's sake, it does make for a good exercise. So that's the reason that we're going to do it. Okay, so the iterative thing, we basically just need to add the numbers 1 plus 2 plus 3 plus 4 plus ... up until we hit a particular number. Okay. But I think what will become clear is that it's actually better to do this counting down from the top than counting up from the bottom. It doesn't really make a difference mathematically because, of course, 1 plus 2 plus 3 plus 4 plus 5 is the same. But I'll show you one when we start here of why it might actually be better to think of it going from the top down rather than the bottom up. And that's more for this processor than for anything. Okay, so what I need to do is let's just make our program, and so let's call it triangle iterative. Okay, and I'm going to have at some point in it, I'm going to have some sort of loop. Okay, right? That's the whole point of doing something iteratively, is that there'll be a loop. We'll worry about initializing and then also what our contents should be. Okay, so let's load something into the accumulator. Okay, and let me just take 5 for sake of example. Okay, and so we'll compute the 5th triangular number, which would be 5 plus 4 plus 3 plus 2 plus 1. And then, well, plus 0, but yeah, okay. And then we'll have that get spit out. Okay, so what I'm going to do then is I'm going to store this to memory address 00, okay? And then so that will put the number 5 out into memory in address, the very, very first address. Okay, and let's remind ourselves, why is it that I need to have 4 symbols here versus only 2 for the load accumulator part? Well, how big is my data bus? It's an 8-bit processor, right? So I can only load 8 bits worth of stuff, and 8 bits requires 2 hex characters. Whereas memory addresses are 16-bit, and so they need 4 hex characters. Now, here I've explicitly typed 4 zeros. I didn't have to do that, but might as well. Okay. The other thing is, what's the difference between a dollar sign? What's the dollar sign signify? Hex. The hash mark signifies immediate value. Okay. But you do not use the immediate value with the memory addresses. Okay, you only use them if you're loading a specific number. If I wanted to load the accumulator from a memory address, I would not have the hash mark. Okay, so that's just I've chosen the number 5 just for sake of demonstration, and that's going to store it out into the first memory, or the first memory address, and then I'll put the answer in the second memory address or someplace else in memory when I'm done. And this will basically take the role of printing, like we did when we did this on the Raspis, where we printed the numbers to the console. I'll just put it in memory instead, because we don't have a console on this simulator to print to. Now on the Commodore we do, and you can use printf basically, yeah, okay. So let's think about how do we pass parameters to functions. Well, how did we do it on ARM? When we wrote a function, how did we pass parameters to it? What was the convention? Yeah, or so we put whatever the thing we were passing to the function in the registers x0 through x7, possibly W0 through W7 if they were 32-bit ints instead of 64-bit ints, or maybe we used S and D or the vector registers depending on the data type. But point being, we had to pass these things through registers, and there was the convention about the order and whatnot that you pass them in. Okay, now we have a mild problem because how many registers do we have for this processor? One or three, depending on how you want to count. Okay, there's the accumulator, and then there are the two index registers X and Y. Okay, now if I want to pass a single number, well, that's fine. I've got the accumulator. I can pass a single number. If I need to pass up to three, I can use the index registers also. Okay, but I can't really pass more than three without also using the stack. Okay, and that's fine, right? In some sense, we had to do the same thing with ARM. It's just that we never had functions that we were passing more than like a couple of values to, right? So we never really had to use the stack for anything that we programmed before. We could have come up with a situation where we did, but we never did in practice. So it wasn't really a worry. For this function, we really only need to pass one value, okay, the value in the accumulator. Okay, and right, okay, so what do we need to do in our loop here? Well, I'm going to use memory address 0001 as basically a temporary storage space, okay? And so I'm going to make sure that it's zeroed out before I start this, because if there's data there and I start adding things and putting data there, then I might get bad values, okay? So I'll just zero it out just to make sure that my butt's covered, basically. Okay, so what I want this thing to do is go to the loop and compute something, and when it comes back from it, store the answer someplace in memory, okay? And I'll just use memory address 0002 as our output address. This will be kind of taking the place of a printf statement when we were doing this in ARM, okay? Because I don't have a console on this machine to print anything, okay? Okay, so does that make sense? Yeah? Okay, so now what we need to do in our function here, okay, or our loop is, well, let me actually change it to, let me just call this one main. That's whatever, and then I'll do that, and then I'll jump to triangle iterative. Oops. Okay, and then I can put some initialization stuff here before we go into the loop. Because, for example, I need to initialize a counter. Okay, so I've got to set that up, and it makes sense to do it inside the iterative function rather than outside. Okay, so where are we going to put this counter? Well, the accumulator is the only register that you can do arithmetic with except for adding or subtracting one. Okay, so the X and the Y registers you can increment and decrement, but you can't do any other real arithmetic on them, general arithmetic. Okay, all of the general arithmetic has to take place with the A register. Okay, okay, so our A register is where most of the arithmetic is going to happen. The X and the Y registers I can increment and decrement basically at will. Okay. So what that means is if I can increment or decrement them using the index registers, that's where I want to put counters. Right? Because there's an instruction, a single instruction that all it does is either add or subtract one from either one of the registers, right? So I guess that's technically 4 instructions. Dex, decrement Y, decrement X, increment X, and increment Y, right? 4 instructions. But those are all real quick, right? Because all they're doing is adding 1 or subtracting 1. Okay, so what do we want to, where is our counter value? Well, let's just use the X register. We could use Y, it doesn't actually matter, right? But what value do we want to put in our counter in this case? Which number? Well, okay, we need to do a counter, right? So if I want to add up the numbers 1 through 5, I need to have a counter that tells me when I'm done. And how should I set up this counter? What should its first value be? Why? I said it was better earlier. Okay, and I'll explain why it's going to be better in a minute. So let me set the X register to be 5. Okay, now I already have the number 5 in the A register. Actually, I don't, because what should I do here? I need to put this, I need to swap the order of these instructions. Okay, good. So 5 is coming in the A register, and I want to put a copy of it in the X register. Okay, so what seems like a good idea? Copy it. How do I copy it to the X register? Yeah. Oh, because if I did this first, it would store the value 5 out to memory, but then when I'd loaded 0, I would be passing 0 to my function, but I wanted to pass 5. There's only one accumulator, right? Okay. So, yeah, okay. So I want to copy what's in the A register, which when I come into this function is right now 5, and I want to copy that to the X register. And so what I'm going to do is I'm going to do TAX, transfer A to X. Okay, that's what the instruction is called. All right, now since there's only 3 registers, like how would we have done this with ARM? How would I have copied something from one register to another? I would have used a move command, right, which is really a copy, but yes. And I would have said move destination, comma, source, right? And that would have copied the data into the appropriate register. But in our case, I've only got 3 registers, right? A, X, and Y, and I can only actually transfer them between X to A and A to Y. I can't transfer directly from X to Y. Well, that sucks. Okay. And so the instructions for transferring are basically all of the form TAX, TAY, TXA, TYA, right? And that transfers from one to the other. So TAX transfers A to X, okay? So that makes a copy of X, okay? Then, so now what's in the X register and what's in the A register are at this moment the same. It's 5, okay? Make sense? Okay, now I'm going to make one other minor adjustment here, which is I need to use the, let's see, how do I want to do this? Okay. Let me store, actually, let me do this. Let me delete this part, and let me just store the number twice. Okay, so this way, and so let me just think for a moment. Okay. Yes, okay. So I'm going to put the number 5 in this memory address. You'll see why in a second. Okay, I'm going to transfer A to X, and then I'm going to decrement X. Okay, and then I'm going to transfer it back. Okay, so now what is in the A registers right here? 4, and what's in the X register? 4, because I decremented first. So 5 came in, I transferred it to X, I decremented, and I transferred it back. So now both registers have 4 in them. Okay? All right, so what I need to do is, at this point, I need to check the thing in the X register. If it's 0, I'm finished. Okay, so let me come out down here and have a done. Okay, and we'll worry about what goes there. So how do I check whether or not I'm done? Compare it to 0. Okay, but here's the thing. We're actually going to end up changing. We will end up deleting that line here in a minute. Okay, and I'll explain why when we get there. Because all the arithmetic set the flags, yes, but we'll get to that in just a second. Okay, so I'm going to compare it to 0, and in the situation that I have equality, then I'm going to jump down to the done. Okay, and in the situation that I don't have equality, then that means I need to keep going, and so I need to do stuff, and then I will have, something that will send me back up to the top of the loop. Okay, so I've got a condition to check, should I keep looping? I need to make the, and then the thing at the bottom is just going to take me up to the back to the top of the loop, and I need to add the loop body next. Okay, so assuming that the X register is not 0, that means we haven't hit the bottom yet. What should we do? Well, what's sitting in the how do I do arithmetic with the A register? I have to add, I can't add X to A or Y to A. What I can do is I can add what's in a memory address to what's already in the accumulator. Okay, so what do I want to do here? I want to add with carry, okay, the value that's in memory address 0001. Okay, does that make sense? So what's in memory address 0001 when we start this thing? 5. What's currently in the A register? 4. So if I do add with carry, the accumulator is now going to have 9 in it. Right? Yes? Okay. And then if the accumulator has 9 in it, what should I do with that number? Store it somewhere. Where should I store it? Let's store it in 0001. Okay, so now what's in the A register? 9. Or, well, and what's in that memory address? 9, okay, because I just computed it and then dumped it out to memory. Good? Okay. Now what? I need to decrement my counter. Not yet, no. But how did I decrement my counter? Yeah, I decremented the counter, and then I'm going to transfer that to there. Okay, so that will subtract 1 for the counter and then overwrite the accumulator with that value. Okay, now how else could I have done this? Could I have put the number -1 out in memory in some place and then just added it to? Yeah. Yes, the order is not the same as it was with ARM. TAX transfers A to X. TXA transfers X to A. Okay, so the order is the way you read it. Okay, and that's just the way that this was designed, right? Sorry. 3, okay. Then I'm going to transfer 3 to A, right? Yeah, okay, but when I transfer X to A, now the accumulator has 3 in it, right? Which means I'm ready to go back and restart my loop. Yeah? Okay, so that should be it for the loop body. Okay? Yeah, exactly. It's going to check again, should I keep looping or not? Okay? Huh? Well, we'll see why I can erase it in a moment. Okay? All right, now, what do we do when we're coming out of the loop? When we're finished, what is the last instruction we need to do? Well, not the stack. The accumulator will have the correct value in it, right? The answer. And where am I storing that when I come back from the function? I chose to put it in memory address 02. So the only thing done needs to do is return from this subroutine. And that instruction is RTS, return from subroutine. Okay? All right, so let me run it and see if this works correctly, first off. And hopefully it will, and I didn't screw anything up. So I'm going to assemble it, and we've got an error. What's the error say? Triangle iterative. Did I misspell it? Oh, yeah, maybe it doesn't like that. Okay, let me just call it triangle. Okay, that's fine. Yeah, it just didn't like the hyphen. Okay, so if I run it, okay, then clearly I have something wrong because what do I get as my answer? Not what I'm supposed to get. Okay. So the point of that was, well, okay, I've been maybe a little inefficient here, which is I'm using A as my the accumulator is where I need to do the arithmetic with, okay, and but the X registers have the auto decrement function, right? So I'm taking, if I put in the number 5, okay, how can I answer your question if you're not in the room? Okay, all right, forget him. All right, so let's see what I've managed to screw up here. Hmm? You've messed something up. Okay, let me reset it and run it. 92. Okay, that is way too big. All right, well, let's see why that's the case. So let me, and we never actually stored the accumulator out to this location, which is interesting. Okay, so here's how we can maybe figure out what's messed up. So let me reset it, and I'm going to go into the debugger. Okay, because what the debugger will let me do is step through basically like we would in GDB. Okay, so if I step, okay, and I execute, I've just executed this instruction. So what's in the accumulator? 5. I'm going to store that to memory, store it to the next memory address, and now I'm going to jump to my subroutine, and you see the program counter is advanced to here, triangle. Okay, so next instruction, transfer A to X. Okay, X now has 5 in it. I'm going to decrement it, and I'm going to transfer it back. Okay, then I'm going to compare X to 0, and on equality, I know I'm finished. We do not have equality, so what's going to happen here? I'm going to add with carry. No, it adds the A register. The A register is the only one that gets arithmetic done with it. Yeah, so it adds the A register to what's in that memory address. Okay, and what do we get? We now have, oh, wait a minute. Yeah, I know, but then how did we get A there? Oh, I know. What is A? 10. All right, I got 10. What should I have gotten? No, 9. Because last time I checked, 5 plus 4 is 9. But I got 10. Why did I get 10 when I should have gotten 9? There was an extra 1 added. Why was there an extra 1 added? Neither. It's because the carry flag was set. So you guys remember in ARM, how many add instructions were there? There were 4, right? And 2 of them, add C and add CS, took into account what the carry flag was, right? Okay, so what happened was the addition took into account a carry flag. And so 9 became 10 because it was 5 plus 4 plus the carry flag. Okay, so what do I need to do to make sure that that doesn't happen? Or clear the carry flag before I do the arithmetic, because I don't know in advance whether or not the carry flag has been cleared. Okay, so what I'm going to do right here is I'm going to clear the carry flag, CLC, clear carry. Okay, now let's rerun it. Okay, still not correct, but you did? Well, 20 hex is 32. Right, which is not the correct answer. Yeah, okay, well, now we just have to figure out why we're wrong, okay? Okay, so let's see. We are, well, so we cleared the carry flag, so let's reset it and step through with the debugger, okay? All right, so X register, decrement, accumulator, the addition is about to happen here. Okay, so we have 9. It's going to get stored out into memory. There it is. Okay, we're about to decrement X to 3. We're going to transfer that to A. We're going to jump back to the start of the loop. Okay, we're going to do the comparison. It's not equal to 0. Okay, so we're not going to do the branch inequality done. We're going to clear the carry flag. There, it just got cleared. We're going to add 3 to what's in memory address 0001. And now we have C, which is 12. Okay. Decrement, come back around. E is 14, right? That makes sense. Okay. So decrement, clobber, come back around. Add, we get F, that's 15. Decrement, okay, so this branch did not take place. It should have, though, because the comparison should have oh, wait, maybe actually it did. Sorry, it did do it. It returned to here. Oh, okay. Let me do this. Actually, I think this is the problem. There we go. Okay. So what I just did is, this is partly because we don't have an operating system. So there's no way to stop execution. Okay. When we were doing this on ARM, if we did a ret at the very end of our program, what happened? We returned to the operating system, and that basically shut everything off. Okay, so what happened is that the program was actually fine. It but so it exited the loop, everything was fine. It came back up here, it stored it into memory, and then it kept executing code because we didn't tell it to basically stop. Okay, so well, there is no end. Well, okay, so I could have made this. Let's just put an RTS here, and that has the same effect in this simulator. Okay, is basically the function, the program is complete. If you RTS from something, like that's the end of it. Okay, but you'll notice that it will say stack emptied wrapping, and then it comes around to, it tries to start executing code at memory address 0, which it can't do. Okay, so this is essentially, there's not really like a halt. Okay, is sort of the issue. Okay, so what I had a minute ago was just when the program is finished, I just put it into an endless loop. Right, so what is that going to do? It's just going to put the program into an endless loop that just sits there forever. But point being, it does so after we finished what we were trying to do. Okay, so it works, right? Okay, so let's think about then. No, it did. That was the problem. So the problem with the carry flag, for whatever reason, was set. Okay, and I needed to make sure to clear my carry. Well, okay, because so the carry flag could have been set by any other operation that was taking place, and or maybe it was set because before I went into my subroutine. I don't know, right? But by clearing the carry, I make sure that I don't have that problem. Okay. Now we could think about and experiment with, what about if I move the clear carry outside the loop? Probably a better place to put it, because right now what I'm doing is clearing the carry every single loop. Okay. But that's something that we could mess with. Okay, so you guys see what the issue was with the carry versus the non-carry? Okay, now, I jump back up to my loop and I do this comparison. And I claim that I could remove this comparison. Okay, and the reason I can get away with that, and that's because of the architecture, is what was the last instruction that I did here? I decremented X. That instruction also sets the flags. And what is the comparison going to do? It's going to check the flags. Okay, and so when I say equal here, really it means equal to 0. Yeah, so comparison is going to set the flags, but the decrement already did that. So if I remove this instruction, it should work identically to what it did a minute ago. And let's just double check. Sure enough, right? Okay, so this is where you can get some efficiencies in here, right? Because the sorry, you don't need to do comparisons all the time. Sometimes you want to, but not always do you need to, okay? Because all the arithmetic instructions set the flags when they're finished, and there's no way to turn that off. If you want to destroy a flag because you don't want it to mess up something, you have to manually clear it. Okay, so there's, and the flags, by the way, are these dudes here, right? There's the the 7 flags, NV, BD, IZC. And the D is for decimal. The 6502 actually could do binary coded decimal. That was not used by a bunch of machines. So for example, the Nintendo, they actually laser fused that part off, like it just doesn't appear at all in the chip. And they were able to get around a patent violation by doing that, which is kind of clever. So yeah. Okay, so does that kind of make sense iteratively? So why was it better for me to go from 5 down than from 1 up? Because comparing to 0 is easy, right? If I had gone from 1 up to 5, I would have had to have a compare 5 up here. Okay, I could restructure the code to do it that way, but then I'm doing a comparison every time. And by structuring it this way, I have to increment or decrement anyway, right? No matter which direction I'm going. And since the increment or decrement are going to update the flags, then I can use that to my advantage to sort of also do a comparison at the same time, right? So I have to like think with portals here. Yeah. Okay. Right. Does that make sense? Okay. So good. Um, so there's our an iterative example. Okay. Is this the only way I could have done it? No, of course not. Because for example, you see how I'm doing the decrement and transferring back and forth between X and A a bunch, right? I could have also stored the number -1 someplace and just added directly to the A register. Okay. But yeah, we would have to think about, well, which would be more efficient? This doing this text as 2-step or doing something else? Okay. So how do I know, by the way, how long it takes for any of these instructions to execute? Well, we look at the manual. All right. So all right. So here's all of the instructions you've got. Literally every one of them. Okay. You can decrement memory, you can decrement X and Y, but you'll notice there's no decrement A. Sorry. Okay. What else do you have? You've got addition, bitwise stuff, branch and carry clear, branch and carry set, branch and equality, bit testing, branch on minus, branch on not equal, branch on plus, break, okay, which causes a non-maskable interrupt, which we won't need. Branch and overflow clear, branch and overflow set, clear carry, clear decimal, clear interrupt, clear overflow, comparisons, decrements, exclusive or, increments, unconditional jump, jump to subroutine, load specific values, logical shift, no op, which does nothing, inclusive or, PHA and PHP are stack operations. PLA and PLP are also stack operations. Rotate left, rotate right, return from interrupt, return from subroutine, subtract with carry, set carry, store A, X, and Y to the stack, or sorry, to memory. Sorry, not the stack. Those are PL, the PL instructions. Okay. Transfer between A and X, A and Y, S and X, which is the stack pointer, X and A, X and S, and Y and A. That's literally the entire instruction set right there. Huh? I just Googled for it, but I think I've got a link on it. I mean, just 6502 opcodes, right? There you go. Okay, so we were doing a decrement X and a transfer X to A operation. So the decrement X takes 2 machine cycles to execute, okay? And the transfer X to A also takes 2 machine cycles to execute. So a total of 4, okay? Had we done addition with memory, okay, and this would have been addition 0 page, right? It would have taken 3 cycles, okay, but we also might have had to clear decimal or clear carry flags, because think about, if I add -1, how do I add -1 on a machine like this? What is -1 represented in hex? It's FF 255, right? So I subtract 1 by really adding 255, right? Well, if I add 255, what's going to happen? Every time I do it, I'm going to get a carry, which means I might have to worry about the carry flag in that situation, right? But doing so requires an instruction that may slow things down, okay? Well, okay, but Rippy, you have to remember, right? How fast did this processor operate? 1 megahertz, roughly, right? And if we're single stepping this or running it on the breadboard, it's operating at like 100 hertz tops, right? That's slow. Yeah. Okay. So it's something you just have to think about, though. Okay, is my point, right? All right. So we just did this iteratively. Now for the fun part, let's do it recursively. All right. So let me take this code and copy it over to my secret document. Okay, and save a copy of that. Okay. All right, so I'm going to delete this, and for the sake of time, I'm just going to put in the finished product, and we'll go through and look at it. Okay, So, so what I'm doing in this program is, well, similar to before, okay? I'm going to load X as the number that I want to use, um, but it'll eventually go to A, okay? So this is slightly different than the way I did it before in the iterative version, but that's okay. I'm going to load X with 6. I'm going to load A with 0 and clear out 3 memory addresses. Okay, that's just to cover my butt because how do I know that there's not already memory there? I'm going to clear the carry flag and then I'm going to transfer X to A. So when I go into the subroutine, A will be the number 6. Okay, and so here what I wanted to do, let me actually change this to 5 from 6. Because I wanted to first store it 0 to these 3 memory addresses just to clear them out. And so I need to have the number 0 somewhere to do that, right? So strictly speaking, I didn't need that, but just to cover my butt, I wanted to make sure that the memory was clear before I did anything. Okay, so store A to 0, the memory address, and so the number 5 would be in the original memory address, okay? And I'm going to initialize A to be 0 before I go into my subroutine. And I'm going to use X as my counter, my index, okay? So X is going to tell me which part of the recursion am I in, okay? Does that make sense? Okay, so when I go into the subroutine, X is the number and A will kind of be my running total slash how I do the arithmetic. Okay, so what is the recursive definition of these triangular numbers? Well, if I want to think of it recursively, right, then I want to say something like, all right, so triangle of int num. So if I did something like this, what is it going to be? If n is less than or equal to 2, or sorry, less than 2, what do I return? What's the first triangular number? 1, right? Okay. In the same way that what was the base case for the Fibonacci's? What were the first 2 values? 1 and 1, right? Okay. Then for the non-base case, okay, Fibonacci is 2 base cases. We only have 1 here, right? What do I need to do elsewise? Okay, so what's my else? I need to compute what? Yeah, I need to compute triangle of n minus 1. Right? I need to take whatever my current number is and return triangle of it minus 1, which means I need to compute n minus 1, then run triangle of it, then get the result back and add it to the current num. Right? Does that make sense? Okay, so how am I doing that here? Well, if I need to, so I need to compute n minus 1, but I also need to keep the value number around. All right, so if I want to keep it around, what is that code for? Got to store it someplace, right? Well, what are our options? The stack or memory, and the stack, of course, is memory, but I can either put it on the stack and pull it off later, okay, or put it in memory some way, where. And I choose to use the stack because I'm doing recursion, and so I don't necessarily know where in memory it needs to go. I'll let the stack pointer keep track of that. Okay, so I'm going to take, so here's my base case. I'm going to compare x to 2. If the comparison is plus, so what does comparison actually do? It does a subtraction, right? So if I subtract 2 from the number, okay, and then branch on plus, when is that going to be plus? If the number is 3 or bigger, or sorry, greater than 2, yeah, okay, which is perfect. That's when I want to do the recursive case, okay, and if it's not the recursive case, well, then I'm just going to load the accumulator with 1 and return. And I'm using the accumulator here as where my return values are going to come from. But they got to go somewhere, right? Okay, and so like with ARM, how did we do this? We put return values in X0. Well, I'm going to put my return value in A, the accumulator. Okay, so I'll load A with 1 because that's the base case return value, and I'll return. Okay, so base case, are we cool? Yeah? Okay, recursive case, that's the fun one. Okay, so I need to put the number onto the stack so that after my recursive call, I can use it. Okay, so I need to push the X value onto the stack. Okay, however, is there a function for putting the X onto the stack? So let's look at our opcode chart. Okay, so STX, what does this do? It stores the X register, but it stores it to memory. Okay, and that's not what I want. I want to put it onto the stack. I don't see a stack instruction that involves the X register. There isn't one. What I do have are these 4 instructions, okay, or well, 6. I can take X and put it in the stack pointer, but that's not what I want to do. I want to actually put it on the stack. But the only way I can put things onto the stack is by pushing the accumulator or the processor status register. But I can only push the accumulator onto the stack. I want to push X onto the stack. So what do I have to do? Exactly. I've got to move the X to the accumulator and then push it onto the stack. Then you better save it because it's about to get clobbered. Okay. So, yes. So if there's something in the accumulator that you need to use to preserve, you better preserve it before you do this because you're about to nuke it. Okay. Okay, so that's exactly what I'm going to do. I'm going to transfer X to the accumulator, then push the accumulator onto the stack. So now the number num, okay, which for our example is 5 at the beginning, right, is now preserved on the stack so that I can take 1 away from the number and branch, go into my recursive call. Okay, so these 2 instructions there, decx is doing num minus 1, and JSR triangle is computing try of whatever. Right, so this is my recursive call. When I come back from it, the answer is sitting in the accumulator. I'm going to put that into the into memory as a for temporary storage, because what do I need to do? I need to pull something off of the stack, right? The original number. So I'm going to pull it off the stack and then move it to the X register. okay? And then I'm going to add with carry what's currently in the A register to what I dumped out into memory. And then I'm done. I can return from my call, okay? So I had to, if I'm going to push something to the stack, what had there damn well better be? A symmetric pop, or pull in this case is what it's called, but pull, pop, whatever, same thing, okay? So if I'm pushing data onto the stack, I need to symmetrically be pulling it off of the stack, okay? And the stack, you really have to be careful here. So remember when we, in 241, how did we kind of think about the stack? Yeah, the magic, the spring-loaded plate holder in the cafeteria, right? You push things, it's last in, first out, or first, yeah, right? So I pop something. Well, yeah, okay. So I push something in, right? And then I'm going to pull something off, right? But the order obviously matters, okay? Well, okay. But it's not immediate because the recursive call happens in between. Yeah, so you, exactly. Okay, so for the recursion, the way this would work, right, is you would go into this recursive call and you're going to push, 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 push down until you hit your base case, and then you're pop, 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 pop coming back off, and eventually, what should be the case when it's all said and done? You've pushed as much as you've popped, and the stack ends up exactly the way it was before you did anything. Okay. Now, how do you know that the stack has been sort of restored to its old status? It's because your stack pointer comes. What does your stack pointer start at always? FF. Okay. And where is the stack in memory on this thing? Page 1. Okay. So if the stack pointer is FF, really that's 0, 1 FF. Okay. But you only have to keep track of the FF part because the 0 and the 1 are hard coded. That is a limitation of the architecture. The 6502, the stack shall be page 1 of memory, period, no arguing. Page 1, because page 0 is the, yeah, it's just, yes, right? Yeah, second in order, but it's page 1, right? Because we start counting with 0 just to keep everybody on their toes, okay? All right, so I pushed, I went into my subroutine call, I came back and I popped, I had used a piece of memory as a piece of temporary storage, okay? And then I did the addition, and that's gonna, when I pop, pop, pop off, that should get it, okay? So what should happen if I assemble and run this stuff? Okay, then what did I get? Where is my answer? I chose to put the answer in memory address 0002, okay, because I was using memory address 0001 as sort of a temporary storage spot, and memory address 0000 I was using for the original number, just so I could see what I had computed, right? So here, the fifth triangular number is 15, which in hex, of course, is F. Hmm? F, yes, okay. Okay, so there we go. Isn't recursion fun? No? Okay, so what's a little irritating here, okay, compared to when we did this in ARM, right? When we did this in ARM, you had a bunch of registers and you could store any of them straight to the stack. In fact, you could store them in pairs, which was kind of handy, right? Or you could store them one at a time, either way. But we don't have that. We can only push a single plate onto the stack at a time, and the plate has to be in your accumulator hand before you can push it onto the stack. So if you want to push 6 things onto the stack, what do you got to do? Well, rigmarole with your hands to get the correct thing in your hand to push it, then go back to the next thing and push it right. So there might be a whole lot of plate, like you might have to be tossing a whole lot of plates up in the air and grabbing the right one at the right time and hoping that you don't let any fall to the ground and break. Okay, so yes, so if you've got to really think about the pushing and popping business. Okay, all right. I wanted to take, for sake of additional demonstration, let's take what I wrote basically there on the board, which is I wrote this in C, right? Well, let's do that and kind of see what CC65 gives us as output. Okay, good. So let me come over and move this here. You here, me here. Okay, and I'm going to open this. Okay, so I have written basically, well, I can get rid of this, but okay, so I have written the same thing, but in C, right? Because what is our function? Well, if it's the base case, return 1, otherwise return the number plus the triangle of the previous one, right? Okay, and here I called it A instead of num, but whatever, right? So this part, right, no big deal, okay? And then my main function is, well, let me just say 5, okay? And I'm going to compute the answer as the triangular number of 5, and then I'm going to print it using printf, same syntax as we've done before, and then I'm going to return basically 0 or X is success back to the operating system. Okay, so no big deal. Now, one thing that's different though is up at the top. So when we did a bunch of stuff in C last semester or previous semesters, right? We had to use we used stuff from the C standard library like printf. Okay, but I'm going to compile this for not just any machine. I'm going to compile it for the Commodore, right? So I want 6502 assembly to be produced, right? Which means I'm not using GCC, but rather CC65. Yeah, it's called CC65. Well, actually, there's several compilers. CC65 is a C2 assembly thing, right? And then there's also an assembler. There are boatloads of different assemblers out there, okay, for 6502 opcodes or to 6502 binaries. Yeah.
How would this? I'm curious to see how that disassembler would react if you gave it like pointers and like the references and stuff. Like, I want to see how that would like trying to disassemble that.
Well,
Because,
okay.
like, you just have like a, for example, an array or like a references and pointers. Like, how is it gonna interpret that?
Hey, look, somebody who's spamming me on the thing. Okay, let's ban them. Block. Oh, there's a bot, that's trying to. Um, okay, so great. Okay, so let's compile this. okay? And the way I'm going to compile it, right, is so I'll pop open my terminal. I also want to use, oops, okay, CC65, okay? And let's go to the documentation, right? And okay, there's a whole bunch of stuff, right, obviously. But what I want to do is I'm going to output to something, okay, and I'm going to have it generate for the target of a Commodore 65, or 64, excuse me. Okay, so I'm going to do CC65, and then the output I want to do, oh, well, first I've got to be in the correct directory. Okay, and here's what I'm going to do. I'm going to do output to triangle.s, target C64, triangle.c is my file. Okay, now what I want to do is I want to go back into Atom and I want to load that assembly, machine produced assembly, and see what we got. And what did I call this? Triangle.s. Here it is. Okay, so let me blow that up so it's a little bit easier to see. Okay, now there's a whole bunch machine produced assembly, right? There's a lot of these headers and blah, blah, blah going on, right? But let's kind of look at in specifically what's going on with the code. Okay, it's not as clear. Let's see, where is it? Here it is. Here's my triangle program. Okay, so what's happening is, so look at right before this. What do I have? Load AXYSP, some sort of subroutine. Okay, that's probably part of the C library for this. And JSR decrement AX1. Okay, so it basically has a bunch of subroutines that do things like, well, what did we do right before our recursive call? We decremented and we pushed to the stack. Okay, and so that's what these things are doing. But this is the trouble with C, or machine produced assembly. Is it at all clear what the hell is going on here? No. Okay. Now, probably with some sort of directive, I could have had it not do this, right? Or tell it, hey, stop being so stupid and give me stuff that I can actually read here. Okay. But in the same way that we could do something in C and then at least sort of briefly suss out what roughly is going on, we kind of have that. Okay, but this is not going to be particularly tight code. All right, and then while we're at it, let me do one other thing here. Is I'm going to do LD65 with the same. Oops. Oh, sorry, CL65, not LD. Wrong command. Okay. So what that generated is, so you guys remember when we were doing things, this is slightly different than GCC. If GCC both compiled, assembled, and linked, it did all three things in one swell foo. Okay? Uh, CC65 is not set up that way. C6065 compiles. There's a separate program that assembles and a third program that links. If you do CL65, that compiles, assembles, and links all in one swell foo. Okay? And I'm going to output, so here, my target is a C64. What kind of thing do I want? I want a program file, which is, okay. And now if I hex dump this, okay, there's a whole bunch of crap there, but if we look up at the very top, what do we see? Okay, and the reason that that's there is because basically what the compiler has done is put a very small basic stub in there to get the program started. Okay, so let me demonstrate that real quick. Rippy, would you sit down, please? Rippy, shut up and sit down. Okay. So I've got this loaded, right? And then I can take, let's see, I want desktop 6502 triangle.program. I'll just drag it over, and then bam, it's printing. Okay. All right. I'll see you guys on Thursday.